Before any of the mathematics, meet the person, Was Solomonoff. Lived from 1926 to 2009 and spent much of his life as an independent researcher, circling a single question. What does it mean to learn from experience in the most general way possible? In the summer of 1956, he was one of the small group at the Dartmouth workshop, the meeting where the phrase artificial intelligence was first coined. And a few years later, in 1960, he wrote a report with a very modest title, A Preliminary Report on a General Theory of Inductive Inference. That plain title hides one of the deepest ideas in the whole theory of prediction.
A general theory of inductive inference. That sounds enormous. What did he actually give us?
He gave us algorithmic probability, a single principled way to assign a prior probability to any hypothesis at all. Remember the North Star we teased at the end of the last episode? A predictor that is provably optimal and provably impossible to compute. This is where it comes from. Solomonoff took the oldest gap in Bayesian reasoning, the question of where your starting beliefs come from, and closed it in principle. The answer even tells us why Occam's razor works. Why, of two explanations that fit the data equally well, the simpler one really is the better bet. To see all that, we first have to look squarely at the gap itself. Bayesian reasoning is a machine for updating beliefs. You start with a prior, some belief about how likely each hypothesis is before you see any data. Then evidence arrives, and the rule tells you exactly how to revise that belief into a posterior. The machine is beautiful, and it is not in question. The whole of science, in a sense, runs on this loop. Believe something, test it, revise. The question Bayes leaves open is what you feed the machine at the very start, before any test has been run.
So the prior is just the belief you begin with. Where is that supposed to come from?
That is exactly the sore spot. Picture two careful people who both hear the same report. A fresh coin has just landed heads 5 times in a row. One of them thinks trick coins are common, so she starts near even odds, and after 5 heads, she is about 97% sure the coin is rigged. The other has handled thousands of honest coins and starts almost certain it is fair. After the very same 5 heads, he still puts the chance it is rigged at only a few percent. Same data, same arithmetic, opposite conclusions. The whole disagreement lives in the prior, and Bayes has nothing to say about who is right. You might answer that the prior comes from earlier experience. But that earlier experience was itself digested by the same updating rule, which means your prior today is really a posterior from yesterday, which needed its own prior the day before. Follow the chain back far enough, and you reach a belief held before any data at all. An original prior, chosen and not derived. For 2 centuries, the honest answer was a shrug. Priors are subjective, pick whatever is convenient. Solomonoff refused to shrug. Here is Solomonoff's move. A hypothesis about a sequence is really a claim that the sequence has some regularity, some pattern you could exploit. And any pattern you can actually describe, you can write down as a program. A recipe that, when you run it, prints the sequence out. So instead of a vague cloud of hypotheses, we get a concrete one. Every hypothesis is a program, and the true explanation of the data is simply whatever program generates it.
Why turn hypotheses into programs of all things? What does that actually buy us?
It buys us a ruler for simplicity. Think back to the last episode, where predicting well and compressing well turned out to be the same skill. A program that prints a sequence is a compressed description of it, and the shortest such program is the tightest description there is. Its length has a name, the Kolmogorov complexity of the sequence. A stream of 1,000 repetitions of the same 2 bits has a tiny shortest program, so we call it simple. A stream of 1,000 truly random bits has no program shorter than just printing them out, so we call it complex. And here is the reassuring part. This ruler barely depends on the computer you run the programs on. Switch to a different machine, and every shortest program changes by at most a fixed translation cost, the same constant for every string. Description length is our measure of simplicity, and it is close to objective. And the space of programs is easy to lay out, once one quiet rule is in place. A program is a finite string of bits that marks its own end. The machine reads bit by bit and knows exactly when it has a complete program, so no program can be the beginning of a longer one. Picture a tree that branches on 0 and 1. Walk down from the root, and the moment you complete a program, you stop. That spot is a leaf, and nothing grows below it. The valid programs are exactly the leaves of this tree. Mathematicians call such a set prefix free. And that one rule keeps the weighing honest. Give each leaf a weight of 1/2 raised to its own depth, and because the leaves never overlap, the total weight across the whole infinite tree can never exceed 1. Most leaves are gibberish, many never halt, but every pattern that could ever be described sits somewhere on this tree, waiting to be weighed. Now we can finally assign the prior base was missing. Give every program, every leaf of that prefix-free tree, a weight set by its length, and let shorter programs count for more. Precisely, a program is weighted by 2 raised to the negative of its length in bits. Every extra bit of description halves the weight. This is Occam's razor, no longer a slogan but a rule. The simpler the explanation, the heavier its prior weight.
So do we just find the single shortest program and go with that one?
Tempting, but no, and this is the elegant part. We do not bet on one program, we keep all of them. The universal prior of a sequence is the total weight of every program that produces it, shorter ones contributing more, longer ones fading away fast. A total the prefix-free rule keeps finite. It is one grand mixture over every computable hypothesis at once, each pulling with a force set by its own simplicity. Nothing consistent with the data is ever thrown away. It is only down-weighted. That is what makes it robust. If the shortest explanation later turns out to be wrong, the next contenders are still in the mixture, ready to take over the moment the evidence favors them. Prediction then falls out by the ordinary Bayesian rule. To score the next bit, you gather the histories that continue with that bit, add up their weight, and divide by the weight of the history you have already seen. That ratio is the predictor's probability for what comes next. Feed it observations one at a time, and it updates itself, with no parameters to tune and no prior left to argue about. This is Solomonoff induction. Now the payoff, and it is a remarkable one. Suppose some genuine computable process is generating your data, and you have no idea which one. Solomonoff's predictor is guaranteed to converge to that true process, whatever it happens to be, and to do it quickly. The total surprise you suffer along the way, the price of not having known the true process in advance, is bounded by the description length of that process. Notice what that means. You never had to know which process was at work, or even guess. You weight your hypotheses by simplicity, mix them, and the predictions steer themselves toward whatever computable rule is really generating the data. One predictor, optimal against every computable source at once.
That sounds too good to be real. What is the catch?
The catch is fatal in practice. The universal prior cannot be computed. To evaluate it exactly, you would have to run every program and know which ones eventually print your data. And that is the halting problem, which no algorithm can solve. There are infinitely many programs, and no way to tell the silent ones from the merely slow. You can creep up on the prior from below, running more programs for longer, but you can never reach it and never know how close you stand. So the ideal predictor is real, optimal, and forever out of reach. Why should that help us? Because it fixes the target. Every practical method we will meet is a bargain struck with this ideal. Keep the mixture over hypotheses, but restrict the hypotheses to something you can actually afford. Count a few recent symbols, and you get engram models. Mix over all tree shapes, and you get context tree weighting. Train a vast network, and you get today's language models. In the next episode, we open up the Bayesian machinery, humming underneath all of them. Prediction as keeping a whole population of hypotheses alive, and letting the evidence decide which ones grow.